Perfect. Okay. Well, thanks very much. Thank you for this opportunity to give the Emmy Noether lecture, and thanks also for rearranging the time. It's 7:45 here, so I've got my coffee, but it's definitely better than midnight because I would not be any good to you at midnight. So I couldn't decide what to talk about today, so I'm going to talk about two things. So this talk has two parts to it. The first part, I'm going to talk about disk tearing and the simulations that I've done of the GW Ori disk. And then the second part, I'm going to talk about simulating the youngest protoplanetary disks. And any of you who were at the Phantom Workshop a few years ago will remember I talked a bit about the radiative transfer approximation approach that we've been using. So I will tell you a little bit more about that. I did want to talk about chemistry as well, but I thought that was a little bit too much to squeeze into 45 minutes. So you've got a two-part, not a three-part talk today. So the GW Orionis disk, some of you might be very familiar with. It's a disk in the, well, broader Orion region. And this star first grabbed attention several decades ago, actually, because it's a dipper star, which means that its luminosity varies, it dips, so it drops in magnitude somewhat erratically, which tells us something interesting was going on. And then we can look at the SED as well, and that's even more interesting still. So on the left here, we've got a figure of its SED. This grey line is the stellar spectra, and each different set of markers or lines on this plot is the SED measured at a different epoch. So this bit of the SED is from the star's light, and this bit is from the disk. And the shorter wavelengths that you go, you're tracing the regions closer to the star. And what we can interpret from this is that the inner disk region is changing shape on very short timescales. So this tells us that this is even more interesting, that there's something really cool going on here. And over the years, it's been possible to tightly constrain the orbits of the stars, taking astrometric and radial velocity measurements at different times over several years. And we found that, well, in 2011, it was found it's actually a triple system. It was known to be a binary, but then a third component was found. And all these orbits are misaligned with respect to each other and with respect to the disk. And they're also quite eccentric. So that indicates we expect to see some interesting dynamics. So in the middle of my PhD, I was given this side project to set up some simulations of this system. Now, today it'd be very easy in Phantom to do. You just stick the orbital parameters into Phantom setup file and it would do the job nicely. I was using SPHNG and it doesn't have that, so I had to calculate some initial velocities and positions to start the stars off. So I ran a model or a few models, took a while to get it going, and found this interesting shape developed. So we got this structure where the inner edge of the disk tore off and formed this ring which precessed round on its own. So as a young PhD student, I looked at that and thought that's weird and also very cool. So I showed my supervisor, Matthew Bate, who thought that was also very cool. And we put in telescope proposals with observers back at Exeter for ALMA and the VLT. And amazingly, we got the time, and it hasn't happened since, unfortunately. Um, but we were very lucky, and we saw this. And this was incredible because it looked surprisingly like the simulation, at least with this middle part. We found this very bright ring, but there's also two more rings and this fainter ring that's several hundred AU out. So I think that's actually the widest known dust ring that's been found in a protoplanetary disk. We don't understand really how these outer ones form, so I'm going to ignore those today, and that's for the future. And then in the VLT image, this is the scattered light. So we're looking at the small grains near the surface of the disk. We can see a very complex, a twisted structure here. And the coolest thing about it is this very narrow shadow here, which is indicating that we've got a tilted ring that's this bit. So this isn't actually face on, it's tilted, but it's also elliptical. So if you look at it at that angle, it actually looks like a circle. And that's casting the shadow across the disk there. So from that, we determined that we were looking at something with this kind of structure. So we can see there's a very steep warp towards this edge here. and then this misaligned ring around the stars in the center. And if you zoom in, that's what the orbits look like. So we took that, we did some kind of analytical type. Um, well, you can put a light source in the middle of it and see what it should look like. And it looked pretty similar to the observations. So from this, we thought, well, is it possible to determine the cause of the tearing? So there are a few options here. It could be just because of the gravitational torques of the host system from those misaligned stellar orbits. Is this evidence of some disruption from some misaligned accretion onto the disk, maybe a past flyby? Or is it possible that there's an embedded planet which has carved out the gap, and then the stellar torques have then twisted that inner ring into a different plane from the outer disk? And I really enjoyed the results of the press releases around that time. So we had nice headlines, well, not quite headlines, in papers and online newspapers and news sources. So if you want to know where to look for this GW Ori star, you look in Orion's nose, apparently. So fine. I didn't even know he had a head. I thought it was just shoulders and a belt. There you go. So to really determine what's going on here, we need to think about what parameters matter in each case. So in terms of tearing just from the stellar orbits, we need to think about the stellar masses, in particular their mass ratios, the various orbital parameters, the disk surface density, and various other disk parameters. The disk temperature profile is important too, so that determines how thick the disk is. If we're thinking about accretion and flybys, we need to think about what are the momentum vectors, how do they affect the orientation of the disk, and as well as the disk properties. And if we have an embedded planet, then as well as the stellar torques, we need to think about what would the mass of the planet be to break it in half, and the thickness of the disk, because that also determines how much of a gap a planet can carve in the disk. So how can we actually try to pull these apart? Well, we could measure the orbits. We've got that. We can measure the disk misalignment. We could try and measure the kinematics from molecular line observations. And on larger scales, if we can observe the gas kinematics, we might be able to see if we've got accretion onto the disk from larger scales. And if there's a planet there, then we could try and detect it. And perhaps we could try having a go at measuring the disk thickness. However, there's a lot of difficulties in doing this. From a theoretical perspective, it was unclear exactly which parameters were required to tear the disk. There are large uncertainties in the observations. Sometimes these are misleading. If you look at the tables of observations, they might tell you that something has a position angle of such and such plus or minus 1 degree. That's not a good thing. So the uncertainty is really related to the fitting process rather than the observations. We can't know position angles, for example, to the nearest degree. There's probably a 5 degree uncertainty in that. We also don't know the history. So it's possible, more than likely, that the disk has been in motion, has been processing for some time. So we don't know how it initially started. Again, if we have a flyby, we don't know, basically. The star could be long gone. It could be scattered by subsequent interactions. It's difficult to tell. And for a planet, it's difficult. So a planet that's big enough to make a gap should be detectable. So that's something positive. But it's very difficult to try and measure disk thickness. Just in a recent year or so, people have been trying to measure the scale height of dust within disks. So that's becoming possible. But this disk is a long way away. So it's about 400 parsecs. And compared to the closer disks that were better characterized, those are about 40, 50 parsecs. So it is challenging. But one of the things we can do is develop theory to have a better understanding of the parameter space that's needed to tear the disk. So to have a start with this, the question is what affects the warp amplitude and braking? And in short, for a circumbinary disk, it's anything that increases the precession torque, which looks something like this. So we've got the binary mass ratio. So if we have a more extreme mass ratio, we get, or if we have a smaller mass ratio, it has a lesser effect than if we have an equal mass binary. It also depends on the surface density. and orbital frequency. So we have a very strong radial dependence. So the torque drops off very quickly to larger radii. And the misalignment angle. So this is then maximum at 45 degrees and drops off quite quickly either side of that. We also need to think about the two different regimes that warps, which are the precursors to tearing, can propagate in. So in more viscous disks, the warp propagates diffusively. However, that's only relevant for very viscous thin disks. So that's not really the regime we're interested in here. For protoplanetary disks, they're thicker. We think the viscosity is very low, and in which case the warp will propagate as a bending wave. And this is quite tricky to simulate because we need to really resolve the thickness of the disk, which requires a huge number of particles. So what we know already is that we expect that tearing is going to occur for about 30 degrees or greater misalignment, depending on various other factors in the disks. We expect thinner disks to break more easily. And other work had shown that protoplanetary disks are probably susceptible to tearing. And other work has shown, including Rebecca's, that embedded planets could break the disk. But not all the previous simulations could fully resolve the wave-like behavior. So we wanted to show that if the disk could tear in the wave-like regime and to test a broader parameter space to get a good understanding of the combinations of parameters that could give rise to tearing. So one of the things that was important was to get proper resolution. And this requires, as I said, a huge number of particles. And you can see an example of why this matters here. You can see that at the lower resolution, that's 100,000 particles, you get a very smooth structure. And then as you increase the particle number, you can actually resolve the tearing here. So we need to resolve the h over h, which is the height, the average smoothing length vertically over the scale height. And we have some equations to try and quantify that. So a few years ago, I did a whole set of high resolution phantom simulations to test a load of different parameters. So these were all 10 million particles. The total binary mass was always 2 solar masses, and the disk was always 0.01 solar masses. The outer radius was the same in all cases, but the viscosity was always smaller than h over r, so it was always wave-like. I'm not going to show you all the results here, so just here's a sample of ones that I think are interesting. And one of them is to do with the temperature profile. So these three simulations all use the same parameters, except the temperature profile has a different exponent. So we set that, here we've got sound speed, as a power law with a radius of minus q. And here we've got q is 0.25, 0.375, and 0.5. And these two disks are flared. This left one is more flared than the middle one. And the one on the right has a constant h over r profile. And you can see that there is a clear difference in the structure. So it's not just how thick the disk is, it's how that thickness changes with radius, changes how the wave propagates through the disk and whether it is likely to break or whether it's just going to produce a gentle warp. Now, protoplanetary disks are expected to have Q between 2 and 3, so we're looking really at the strongly flared side, which is going to suppress any breaking. Another interesting point was looking at where does the disk break. So there are some analytical approaches to estimating this from comparing communication timescales, so how fast the wave propagates through the disk, with precession timescales. And this gives values for the various simulations that I did that are all quite small. So in this case, between 3 and 5 AU. But in the simulations, we measured the break radius to be considerably higher than that. So there is a very big difference between the predictions and what the simulations show. And we think the reason for this is because it's to do with how the assumptions that go into that prediction. So in more viscous disks, which was the starting point for studying disk tearing, the torques are applied locally in the disk, and because the warp diffuses very quickly, it's the local torques that are most important. And that's the assumption that goes into these predictions as well. However, we find that the warping at a point in the disk is due not only to the local torques applied from the start at that point in the disk, but also from the warp that's traveled through the disk outwards. So we can see what's going on more clearly in these plots. So we've got the radius on the y-axis, and the x-axis is the time. So time's increasing along here. And this is showing for different values of the misalignment of the disk. And the color scale is the warp amplitude. So we can see there's a warp being launched initially at the inner edge. Now, some of that is just initial disturbances that settles down with time. But crucially, we can see that there is the warps propagating outwards. And once we get a break, so in this one and these two here, it effectively becomes trapped. So the break is very effective at stopping the wave propagation through the disk. And once that happens, we basically see next to no warping outwards of that. And that's because the precession torque driven by those stars, the stellar orbits, drops off very quickly with radius. So it becomes very weak very quickly. But we can get some warping due to the warp traveling outwards. So really the disk is shaped by the torque that's applied right in the innermost regions and then propagating outwards. So we can get breaking much further out than we'd assume from basic analytical predictions. So back to GW Ori, we've thought about what combinations of parameters might give rise to tearing, and we can now apply that to what we know about the GW Ori system. So the orbits are very well characterized now. The disk orientation is fairly well understood. So the question, can we discount tearing? In science, we can never prove anything, right? We can only disprove something. And the way to disprove tearing solely by the stellar torques would be to choose the most extreme parameters that would give rise to tearing that are allowed from the observations, and to simulate those and to see what happens. And that's what I did. So I looked at the uncertainties crudely that we have in the observations and worked out what was the largest mass ratio we could get, and what was the largest orbital radius, for example, we could get, and the biggest misalignment that we could get from the observational parameters. So the misalignment that I used was 34 degrees. I also tried a retrograde disk. And the reason for this is that if you have a disk that's tilted towards you on the sky, there's a degeneracy between it rotating prograde and being tilted one way, and being tilted away from you and rotating retrograde on the sky. And we can't necessarily be sure which way round it is for other reasons. So it was worthwhile to test if it was actually retrograde. And that would be really cool if it was. So these are the results I got. I was able to do 3 simulations. We tried 0.03 for H over R, and then a slightly thicker disk with 0.04. I did want to try H over R as 0.05, but it was so slow, it was just not going to get anywhere anytime soon. And then the retrograde, I was able to do a thicker disk because it evolves a lot more quickly. So we can see, first of all, that we do get tearing in all cases. And we can see that the retrograde case looks qualitatively different to the other two. We can see that the inner ring quickly precesses to become edge on. And that's not what we observe. So I think we can discount that one and say that, unfortunately, it would be really cool. The GW Ori disk is not retrograde. Now we've got plots here of the warp amplitude against time. And here at the bottom, we've got break radius. So for the retrograde disk, it breaks very close to the center. Again, that's not what we observe. The inner ring location from observations is here in the peach line, so it's about 45 AU, give or take. The thinner disk breaks at about that radius, so that wouldn't allow enough room for the ring to build up. So tentatively, we could very tentatively say that perhaps the thicker disk better matches the observations. But the main point is that we've shown that with good resolution, with different parameters, we can tear the GW Ori disk with what we derived from observations. So we did actually manage to get some more CO observations, and they are a little bit difficult to interpret. These are a larger scale on the sky than the previous ones. And what's really striking is that we can see there's almost this tail structure. Now, I'm not an observer, we haven't analysed this in detail, but this could be foreground or background contamination, but it does kind of look connected to this, and the velocities match up with the rotation of the disk as well. So it's possible that what we're looking at is some kind of late accretion event, and that would explain the disrupted and tilted disk structure. And it reminded me of this. So this is a little simulation that I did as part of a different project where we've got a star and then this cloud is moving across it. And we get this new disk formed in the center and it's peeling off bits of gas from this cloud that's passing through. And we're getting a misaligned outer disk gradually forming as well. So this could be the kind of thing that we have going on. So the part one summary is the takeaway points that I'd like to remember is that it's a combination of parameters that matters more than any single parameter when it comes to disk tearing. So observers would really like us to say to them, yes, any misalignment bigger than 30 degrees will tear. Unfortunately, we can't say that. We need to think about the temperature profile, the orbits of the stars, the eccentricity is important as well. The warping of the protoplanetary disk is mainly due to outward propagation of the warp wave rather than the torques applied at that point in time. We also found that the relationship between the break radius and the disk properties is not clear, so be aware of any very more simple analytical equations for that. And we found that we can explain the GWR structure by disk tearing. If you're into knitting, you should definitely look at this. If you Google knit the universe, you can actually knit the GWRE disk. And one of the PhD students back at Edinburgh did this. So it's possible. You can get the knitting pattern and make yourself a nice disk. So go and do that. Part two then. So next we're going to move from probably a slightly older T-Tauri disk to thinking about the very youngest disks, what they're like soon after they formed. So we're going back in time now, to closer to the beginning where the star forms. So in star formation, we get a pre-stellar core that collapses under its own gravity. We get the stellar core formed in the center, and the inner envelope accretes and forms this rotating disk around the central star. Now, just a few years ago, we weren't even sure that there were disks in this earliest class zero phase. The name class zero tells us what's true in that the class zero phase wasn't discovered till after the class one phase, that the stellar core formed earlier, and we had this earlier stage where this disk was beginning to form. We now know we do have disks in the class zero phase, and they're very deeply embedded, which is why they're hard to detect. As the envelope accretes onto the disk, it becomes much easier to see the disk. We get the class one phase. This is when jets really begin to be launched. And this all happens before 1 megayear. Gradually, more of the envelope accretes, and then we begin to see these class two disks. And these are the ones that typically we're familiar with through like the ALMA D-sharp program that have nice gaps and rings and all these cool structures. And eventually we get a planetary system, debris disks, and all that kind of thing. But we're not interested in that. We're interested in the very earliest stages here. So we know that protoplanets are already quite massive in class 2 disks because we have some really cool observations of them. And this is one of my favorites because we can actually observe the position of that protoplanet in different epochs and show that it's moved and calculate its orbit and show that it's not just some random blob in the disk, it is a planet. And this tells us that the planets must have formed very quickly and begun growing very early. So that pushes the beginning of planet formation right back to class 1 and even class 0 disks. And that's strong motivation for studying what disks are like in those early stages. And disks at the earliest stages are much more massive than they are in class 2, which we've typically in the past simulated. The disk mass can be over a tenth of the mass of the star compared to kind of 1%, which is the typical value taken for older disks. And when the mass is this big, the vertical structure becomes kind of squeezed, so we reduce the scale height of the disk. The self-gravity of the disk becomes dynamically important, and the disk can then be susceptible to the development of the gravitational instability, and that can then be a key source of heating and turbulence within the disk. And we tend to quantify that using what's known as 2 raised Q parameter. And that's a ratio between the thermal pressure in the disk and the shear, which acts to rip apart any kind of clumps that form, and the self-gravity. So this term is the surface density of the disk as well as the gravitational parameter. So that's how much the disk is wanting to collapse. And the top term is how much it's kind of pushing back against that collapse. So that determines the stability of the disk. But whether it fragments or not depends on its cooling rates, which we tend to parameterize using a cooling time as well as the orbital frequency of the disk. So these are all very young. So this all occurs before half a megayear, give or take. But it's possible that with late infall, we could get this massive kind of disks much later on. And I think we do observe a couple of those. More on that later. So because of the self-gravity of the disk and the development of gravitational stability and the mass, we can't just use an isothermal disk profile like we do for older disks. We really need to think about the thermodynamics. Now, I'm sure if you might have been here a couple of years ago when we're in Melbourne, and I gave quite an in-depth talk about this method. I'm not going to do that again now, so the brief overview of what we do is here. So we use a polytropic cooling approach, and it works something like this. So if you imagine we have a spherical gas cloud, and we want a particle in that cloud, we want to know how quickly this particle is cooling due to radiating away to the outside world. And we want to know the optical depth here, and to get that, we have the column density of that particle, so how embedded it is in that cloud. And we've got a table of opacities. So once we know the column density, we can then find the optical depth. Once we've got the optical depth, we can estimate a radiative cooling rate or heating because we know the temperature of these particles. And once we have that, we can use that to calculate an equilibrium temperature given the PDV heating locally, as well as that radiative cooling or heating if we've got an external source of radiation. At this point, we can also include stellar heating, so we can have a background temperature that's either constant across the whole thing or is radially dependent to imitate stellar irradiation. We can also include a diffusion term for increased accuracy. We also include flux limited diffusion, so we can get some heat dispersion in a more local level. And then we can update the energy in the model from all that. We improved on this slightly by moving from spherical geometry to using the pressure gradient to estimate how embedded the particle is in the gas cloud. And then from that, we've modified it again to account for the self-gravitating disk structure. More details are in this paper, but we get pretty good estimates now of the column density throughout the disk structure, which then gives us good estimates of the optical depth. So the next step then is to see what difference this makes. So on the left-hand column, we've got simulations of disks that use the older method. So that's where we have a kind of spherical cloud. And then we've got the new method, modified Lombardi, we call it, on the right, where we use the pressure gradient and adjust for the geometry of a self-gravitating disk. And we do see some clear differences. So for disks before, like this one that developed a kind of grand design spiral structure, we found were actually pretty stable and show no sign of the gravitational instability acting. For other ones, we saw that we got some fragmentation in the outer disk, whereas before it was stable. And yeah, some were completely stable, whereas before we saw quite strong evidence of GI. And the key point is these are all irradiators as well. We are taking into account the irradiation from the central star heating the disk. And I think the key reason for this is how the temperatures are set in the disk midplane. So here we're going to focus on the red line and the yellow line. We'll just ignore the other two for now. And we can see that in these models, the surface density profile starts off and is very similar for quite a long time. So when Q is lower, the disk is more unstable, and when it dips below around 1, the disk is susceptible to fragmentation. And we can see the red line, the older model, becomes a lot more unstable than the previous ones. And whoops, a daisy. The reason for this is that the mid-plane optical depth estimate is quite different with the older model. So we can see that it's a factor of a few to a factor of 10 greater than in the more accurate models. And this gives rise to quite a different mid-plane temperature. So because the mid-plane optical depth is much greater, we're getting greater extinction of the stellar irradiation, which gives us a colder mid-plane, that red line here. And a colder mid-plane is there more susceptible to developing the instability and the fragmentation. So that's really what's driving the differences in this case. So here we've got the alpha due to gravity. So that's telling us that the gravitational torques are stronger in that older model. So using this, we can then go ahead and study the parameter space using our improved model to understand what difference that makes to our understanding of what kind of disks become unstable to GI. And one of the issues is this. So we've got the luminosity versus age of very, very young stars. So the theory behind this is still a bit shaky. So this is a guideline really more than anything. So at 1 megayear, that's here, we can see this is the luminosity of a solar mass star is about, what's that, 2 or something. So as you go back in time, the luminosity increases quite a lot. So very young stars are very luminous, and then you've got the accretion luminosity on top of that. And because of this increased luminosity, that heats the disk a lot more and will stabilize the disk. So we've got a play-off here between the increased mass earlier stages and the increased luminosity that's going to heat up the disk and balance any gravitational stability earlier on. So for these simulations, we pick 0.5 megayears to start with, which seems a reasonable approach. We test a range of disk to star mass ratios, and we test these low mass stars between 0.1 and 1 solar masses. We note that the stars are still accreting at this point, so that will not necessarily be their final mass. So from previous theory, we expect fragmentation to occur only at larger radii beyond 70 AU, and that's because that's where the disk can cool efficiently to generate these fragments. We might expect to see long-lived spirals, so the gravitational stability can lead to this self-regulating state where the spiral arms form when the disk becomes unstable, and then the heat generated by that instability then causes the disk to stabilize again as it heats up, and that process can repeat over and over again. But there's been some debate as to whether that's actually possible. We expect to see that irradiation suppresses the gravitational stability, but by how much, we don't necessarily know. We've seen in some previous work that we know without the irradiation, the GI is much stronger, but it's quickly killed off once you have a very luminous star. So here's some results that we got from that. We found that we can get long-lived spirals. So here we've got a 1 solar mass star, and at half a megayear, the luminosity is about 3.3 solar luminosities. And I was able to run this for about 20 orbits, and we found that the spiral structures come and go. We get different numbers of spiral arms, but on that time scale, they don't dissipate. So it's not just an artifact of poor assumptions or fixed values of beta, the cooling rate with radius. When we have self-consistent thermodynamics, we do still see these long-lived spirals. We've already seen that. So we've got samples now of different simulations with different parameters and the different structures that they show. These are sorted by the color scale that they needed to show up the structure rather than anything sensible, unfortunately. But we found that in the compact disks, we get them stable because of that irradiation at very high disk to star mass ratios. So thanks to the irradiation, we can get stable disks even with 80% of the mass of the central star. So that's a large, really large amount of material that's available for planet formation at those early stages. We do get these big spirals formed, and we do see fragmentation even in these more compact disks of even 50 AU. So we do see fragmentation at smaller radii than 70 AU, a typical value. Going to slightly larger disks, so the masses are the same basically as a smaller disk, so the surface density is lower. And suddenly we find we don't see these large scale spiral structures. We see what I'm going to call faint spirals. If you could squint from the other side of the world, you might be able to see very small indications of spiral structures. But these disks either tend to generally be smooth or they fragment quite quickly. So these white numbers, that's the number of orbits shown in the snapshot or outer rotation periods in the snapshot. So these fragment very, very quickly. Now looking at the whole parameter space I studied, and this gives us a feel for how the parameters affect the fragmentation or spiral structures formed within the disk. So F is for fragmentation, spirals is spirals, and pentagons indicate faint spirals. The black is our new method and the red is the older method. So I ran both of these just to make sure the parameters were the same. And we see fragmentation, as I pointed out earlier, in disks or that are compact, which is really interesting. But the differences come in as well in these larger disks. So we see that we don't get many large scale spirals at all. So we get one up here when we go to quite an extreme disk to star mass ratio where the disk is significantly heavier than the star. And again up here as well. But generally it's either very faint spirals or fragments, whereas before in the red we were seeing quite a few instances of large scale spiral structures. We can also support more massive disks than we could previously in some cases. So there's some interesting results there. It's key, I think, that we see spirals forming for a much narrower range of parameters. And this could explain why spirals are so rare. We have got a couple of examples of spirals that we think are very likely driven by GI, and here's some that are probably familiar to you. And these are probably infill driven, and they're also a bit older. So these aren't the youngest disks. These are much older and probably have had more mass added later, which might be driving that instability. But the typical signature of GI until now has been these large scale spirals, and it's been a puzzle that we haven't really observed that. And perhaps this is the reason that there are GI disks out there. They're just not showing these large scale spirals. So we're not looking for the right thing necessarily. So the summary for part two is that the evolution of massive young disks is slightly different when we use more accurate thermodynamics, and we find that spiral structures might be less common than we assumed. And because compact disks might also fragment, and larger disks can reach higher masses while remaining stable, we might expect fragmentation and gravitational stability to form more planets or contribute to the formation of more planets than we previously thought. So on this exoplanet population plot, we've got the most massive disks on very wide orbits up here. And this is typically the planets that we need GI to explain, the ones that are typically directly imaged. But it's possible that we may be looking at some of these closer in planets too, as to be formed by GI. So back in February in the UK, we had a special discussion meeting at RAS on gravitational stability in disks. So I asked the audience what kind of planets they thought were formed by GI disks. And it was interesting to see lots of people voted for, they could have more than one vote, by the way. We didn't have hundreds of people there. Lots of people thought that they could form smaller planets on shorter orbits as well. I will note there were some people in the audience who were just interested folks from London, so that might account for some of the people who think that every single planet in the solar system was formed by GI. I don't think that's the case, just to put that out there. I also asked, because we have an audience of theorists here, I thought it'd be interesting. Here's some answers that I got when I asked, what do observers need from theorists? And here are some of their answers, as well as the strange ones. I think it's probably useful to bear in mind when we're writing papers, that they don't want code units. I know we know that there's difficulties sometimes in giving real physical units, but they would quite like some physical units, please, and testable predictions, and they want target lists, although I don't know how we're supposed to know what targets to tell them. So I think on a completely different note that it's quite useful to have ideas of how to improve the dialogue between theorists and observers. Um, I don't agree with less equations, mainly because it's fewer, isn't it? Not less. But observers have plenty of equations in their papers too sometimes. So I'll leave it there. And thanks again for inviting me to give this talk. And I think hopefully we've got a few minutes. If there's any questions, I can try and answer them.
Thank you very much for the talk, Alison. You've talked a lot about GI in very young disks. What about core accretion, though? Can it happen at these young ages?
Well, for core, yeah, it's so that's something that we're thinking about as well because for core accretion, I think people are thinking a lot about the streaming instability in beginning that. And it's whether that can happen at these young stages because the disks are more turbulent, which might disrupt it. But yeah, it's likely that if we have GI structures in the disk, that could help the core accretion scenario because we can get dust concentrating in spiral structures and forming rings. So that could assist that scenario. But yeah, we do think core accretion is still the way that most planets are formed. Does that answer the question?
Yes, perfectly. Can I follow up?
Yeah.
Do you have any plan to include dust in your simulations?
I do. That was the point of my fellowship, which I'm now nearly a year in. So I am beginning to look at that, yes.
Okay, great.
Any other question? Beck.
Thanks for a lovely talk, Alison, and congratulations on getting the prize talk. Very well deserved. I wanted to ask about GW Ori. The simulations you ran with 10 million particles. I'm not at all surprised that the H over R of 0.05 took forever to run. That sounds very challenging. But we do expect protoplanetary disks to be a bit thicker than 0.04. Can you comment on what expectation you have for a disk that has an aspect ratio of 0.05 in that kind of simulation?
Well, it could break. We don't know until we do it. It's possible. I think it would take, we know it would take a lot longer. So we would require it to run for hundreds and hundreds of orbits, which is not possible. We do have an upper limit, though, I think. Was it Rubago 2023? I can't remember. One of these papers did 0.07, I think, and found that that didn't break. So we have that upper limit on it for sure. But what happens between, we can't be certain.
Thank you.
Daniel?
I can follow up on that. I mean, so is there any special reason why GW Ori's disk should be sort of thinner than usual? Like from the irradiation, is it especially low mass or anything? Or high mass or
Well, it's unusually massive, so it's possible that self-gravity is kicking in. Because what is the mass of it? It's significantly more massive than most planetary disks should be. So we don't know exactly. It would be useful to get a better handle on the mass. But there's a lot we don't know.
so it does make your aspect ratio a little bit thinner if you got more mass generally, but
Yeah.
0.07 sort of plausible. I mean, like Beck, I'm a little uncomfortable with 0.03, 0.04. If you really can do it at higher H&R as well, it seems reasonable.
Yeah. I mean, the other thing to remember is it's not a stable, smooth disk. It's, as we saw in the scattered light image, it's very disrupted. So again, I mean, it's limited what we can actually simulate because we know that these smooth disks are unrealistic anyway. And if we've got a non-smooth structure, that's going to be more likely to break because we have discontinuities. Well, not discontinuity. We have not a smooth surface density with radius, which is going to affect how warps propagate through a disk.